Okay. So the next talk will be by Julien Salmon, and he'll be talking about lunar accretion from disks produced by non-canonical impacts. And here's the lovely and talented Julien Salmon. So
thank you, Bill. That was lovely. Okay, do I have to do something here? Oh, there you go. So as Bill said, I'm going to talk to you a little bit about accretion of the moon from the prolunar disk. This is the work I've done with Robin Canup, and before anything else, I'd like to thank Survey for making this science possible through our Institute for Science of Exploration Target, that is led by Bill Butke here. So, is this working? Yes, I can change slide. Excellent. So, one of the big problems of the canonical impact scenario for the formation of the moon was the compositional issue that was linked to the fact that this kind of impact form a disk that is composed primarily of impactor material, so that the moon should resemble more the impactor than the Earth. So an alternate kind of impacts called the non-canonical have been proposed in 2012, involving either larger impactors, scenario proposed by Robin Canup, or small impactors but with very high impact velocities, as proposed by Chuck and Stewart. These impacts have produced more compact disks, where most of the mass of the disk is located inside the Roche limit, and they have the great advantage of forming a disk with a composition that is close to that of the post-impact Earth, which could naturally explain the Earth-Moon isotopic similarities, in particular for oxygen. So we still want to raise a number of concerns regarding these alternative impacts. The first one, this is results that we got from a study we did thanks to NRSI of the accretion of the moon for canonical disks. And one of the results of this study was that the fraction of the disk that is located inside the Roche limit is in general poorly assembled into the moon. As you can see here, this is a fraction of the mass of the disk inside the Roche limit that is accreted into the moon, and you can see that in general, less than 30% of this material ends up onto the moon, and 70% ends up onto the Earth. So if these new disks are more compact with most of the mass inside the Roche limit, this could bring an issue regarding as to whether we can form objects of a lunar mass. Second problem of this new kind of impacts is that they leave the Earth-Moon system with an excess of angular momentum that needs to be subsequently drained thanks to a resonance called the evection resonance between the Earth, the Moon, and the Sun. And it has been argued that it could decrease the angular momentum of the Earth-Moon system by a factor of 2. However, the capture of the Moon into this resonance is very sensitive to the Moon's orbital parameters. So estimating these parameters correctly is essential to assess whether this capture could be efficient. So the questions we want to address here is basically, can we form lunar mass objects regarding our concern number 1, and would the Moon initial orbital parameters would be compatible with the capture into the evection resonance? So in order to address this issue, we've expanded a model we developed for the study of a canonical disk that we published in 2012. So based on dynamical and thermodynamical consideration, it is appropriate to represent the prolunar disk via a hybrid modelization, where the inner disk inside the Roche limit here at 2.9 Earth radii is represented by a uniform fluid disk, whereas all the material outside of the Roche limit is represented by a collection of individual particles whose orbital evolution is tracked thanks to the n-body code SIMBA. And we have several interactions between these two disks, in particular at the Lindblad resonances. So in a little bit more detail, for the evolution of the disk, for the material inside the Roche limit, we adopt the modeling of Thompson and Stevenson, where we assume that the disk is a mixture of vapor and liquid, with both phases being well mixed and co-evolving. This disk is going to viscously spread with a viscosity that is limited by the disk's own ability to cool because it's very hot. Due to this viscous spreading, the disk is going to lose mass onto the Earth, but it's also going to bring mass through the Roche limit, at which point this material can form new moonlets that are added to the n-body section of the code. So basically, this disk is going to, thanks to viscous spreading, produce new building blocks to create the moon. As I mentioned, the inner disk and outer moonlets interact through the strongest Lindblad resonance, which cause the outer objects to be repelled and go farther away from the disk, while the inner disk is going to be confined inside the Roche limit. Due to the very fast rotation of the Earth after the impact, it's very oblate and thus has a very high J2, about 100 times what it is today. This very high J2 has several effects. It causes orbital precession of moon-forming objects. It also separates mean motion resonances, and it also moves the evection resonance outward. But the presence of the Roche-interior disk also has a similar effect. This equation here gives you the precession rate of the lunar perigee. When this precession rate is equal to 1 year, that's where you have the evection resonance. And you can see that this precession rate is a combination of a term due to the Earth, thanks to its J2, but also another term due to the presence of the prolunar disk. So the prolunar disk is going to have an effect which is similar to simply increasing the Earth's J2, so it's going to move the evection initially substantially outward. However, as the disk dissipates, this term is going to get smaller and smaller, eventually dissipate completely, and the evection is going to move inward. So I'm going to now show you, so this is just a summary of the simulation protocol that we use. We based our simulation protocol on the successful cases of both papers by Canup and Chuggett-Stewart. We defined successful as the impacts that form disk whose composition shows the least deviation from the post-impact Earth. And so if we can play the movie, there you go. So very rapidly, all the material initially inside the outer disk is accreted to form one big object that has confined the inner disk inside the Roche limit. This disk spreads viscously slowly until it reaches the Roche limit and starts producing new objects. These objects in turn are pushed by the disk and can collide with the moon, but they can also later on be scattered by the moon or be trapped in mean motion resonance and serve as an angular momentum relay between the inner disk and the moon, so that the moon semi-major axis is increased beyond what could be simply achieved by direct interaction with the prolunar disk. There you go. So if we look at the evolution of the mass of the moon through this accretion process, it occurs in 3 consecutive stages. The solid line here is the mass of the moon, and that's interesting. It has a mind of its own. Okay. So the solid line here is the mass of the moon, and the dashed line, the fraction of its mass that is derived from the inner disk. So you can see that initially in the first phase you accrete all the material from the outer disk. The mass fraction of this material remains 0. And nothing happened for several tens of years as the inner disk has been confined inside the Roche limits and needs to spread viscously. And when this happens and the disk reaches the Roche limit, it produces new objects, and the material from the inner disk can then subsequently be accreted on the moon, with overall accretion timescale of several hundreds of years, which is similar to what was observed for canonical disks. A summary of the moon characteristics we found from our different set of simulation. We form, on average, an object of roughly 0.7 lunar masses, which is a little smaller than what we got in canonical disks. This is mainly due to the fact that we have more compact disks and we have this poor accretion efficiency that I've talked to you early on. We do not form multi-moon cases. By multi-moon, I mean forming a system with like roughly 2 half-lunar mass objects. This is also due to the compactness of the disk, because as soon as you have a big object growing, it's going to accrete everything close to him and not allowing for another large object to grow. And we find also semi-major axes that are larger than in canonical cases. However, if you restrain ourselves to the roughly lunar mass objects, this occurs in 6 out of the 31 runs that we considered, and they have semi-major axes that are smaller than the overall average, but still larger than what we found in canonical case. So why is that? So this graph shows in green the semi-major axis of the growing moon, and in red the position of several of its mean motion resonances, here the 2-to-1, the 3-to-1, etc. And the black dots here represent the semi-major axis of secondary objects in the simulation. And you can see that the moon traps in mean motion resonances consecutively different objects. And since these objects are being pushed by the disk, and they're trapped in resonance with the moon, they drive the moon's semi-major axis farther away. And here the high J2 increases the stability of capture into these mean motion resonances, which is why we reach this high semi-major axis. Thank you. Now, where do we stand with the two constants that I've raised initially? So we do form lunar mass objects here, but they seem to require a very, very massive disk of order 2.75 lunar masses, which such masses are obtained in a fairly big amount of the disk proposed by CANUP, but only in roughly 2 of the 22 disks proposed by Turk and Stewart. Secondly, concerning the evection resonance, here I've plotted the precession period of the moon throughout the simulation. The evection resonance here again is at 1 year. So you can see the precession period increases as the moon orbit expands, but as well as the inner disk dissipates. But the moon is still inside the evection by the end of its accretion. However, the studies of encounter with of the moon with the evection only assume that the moon would encounter the evection by expansion of its semi-major axis through tides. But if the solar dissipation of the prolunar disk will also cause the precession period of the moon to increase, so that on this graph I've showed here the precession period of the moon as a function of the remainder of the disk mass, and without a single tidal evolution, the moon could actually cross the position of the evection solely due to the dissipation of this inner disk. I want to point out a few model limitations. Most importantly, the fact that we do not include tidal dissipation, which will affect the orbital parameters of the growing moon, and will thus affect the likelihood of capture into the evection resonance. This is something that we're working on at the moment, and that we will include in further modeling. So to sum up, we do find that non-canonical disks can produce lunar mass objects, but they seem to require very massive disks that may not be obtained in some non-canonical impact scenarios. And we point out that the encounter with evection resonance will be a combination of the moon outward migration due to tide, but also of the resonance moving inward due to the dissipation of the disk. And this is an issue that needs to be investigated closely. Thank you.
Okay, we have time for questions. I don't know if I see a question out there. Well, I will ask a question.
Oh, no.
Even though you're in our group. No, so I mean, another way to maybe say some of the things you're talking about here is that we're starting to get a very complicated model to try to get everything to work with all the different parameters. And the more complicated it gets and the more knobs you add in, the more the probabilities are going to go down. So you want to talk about that a little bit.
Well, it's the thing that is interesting to me for the formation of the moon is that there are I think there are two separate constraints, which are the dynamical constraint and the compositional constraint. And it seems that with the canonical impacts, we have very good dynamical probability, but we have an issue with the composition that we need to address with like equilibration or arguing for an impactor that has a composition close to the Earth, etc. So, once there are strengths and weaknesses, so then we decided to try these non-canonical impacts to resolve the composition. So now the composition works naturally, but we need this evection resonance to, so the dynamical aspects have been weakened by the necessity to invoke the evection resonance. So it doesn't seem that for the moment we have a clear, simple way of explaining both the dynamical and compositional constraint for the formation of the moon. So that means there's still work to be done. Great. We don't have a job.
That's right. So does it mean if you solve it, I get to fire you?
Yes.
All right. So we figured that out. Okay. Any other questions?